So away we go here. All right. So before we jump into calculus with inverse trigonometric functions, we're going to remind ourselves how to evaluate inverse trigonometric functions. Okay. So why don't you go ahead and go A through F there, see what you can accomplish. All right. So see what you can figure out, what you can remember. So go ahead and give those a try. Okay. A through F. See what you can remember how to do there. Okay. See what you can remember how to do. I'll give you like, a minute or two. All right. But go ahead and just give those a try. See what you can remember about how to evaluate inverse trig. Okay. If you need a little bit of help getting started, remember that inverse trig is the reverse of trig. So when I ask the question, what is the arc sine of -1/2? Okay. When I ask the question, what is the arc sine of -1/2? That's going to equal some angle theta. Okay. When we evaluate trigonometry, like normal trigonometry, like sine, cosine, tangent, we are inputting an angle, outputting a ratio. Input is an angle, theta, output is a ratio, right? For the inverse trig, it is the exact reverse of that. We input a ratio, we output the matching angle that would give us that ratio. So another way to think about this is to say sine of theta equals -1/2, or sine of what equals -1/2. So that's another way to think about it, okay? Likewise for B, cosine of what gives us 0. For C, tangent of what gives us √3, so on and so forth for the rest of those. Okay? And if it's helpful to rewrite them in this fashion to help you figure it out, feel free to do that. But again, I'll give you like a minute or two to figure it out, and I'll kind of walk around if you want to ask me a question privately, not in front of the whole class. Bless you. Remember that these have some different ranges and things too, right? Some of these functions you want to give like negative angle measures. Some of these functions you want to give angle measures that are in the second quadrant. All right, so I'll help you out with that too. Sine, arc sine and arctangent, okay, if they're negatives, then you want to give the angles in the not fourth quadrant, you want to give the negative versions, I guess, of the angles, okay? So arc sine and arctangent, if you're taking arc sine of a negative, you want to give the negative version of that angle. But if it's arc cosine, you want to give the second quad. If arc cosine of a negative, you want to give the second quadrant version of that angle. So keep that in mind there. Okay. So let's push through here. All right. So letter A, what would theta have to be here? What do we say? Simeon? Okay. So say again.
-1/2.
Right, negative pi over 6 in this for the inverse trig functions, right. We want our theta to be negative pi over 6, okay? Another thing that's helpful when you want to evaluate these inverse trig, you can use your reference triangles too. So, sine of what angle gives us negative 1/2? Well, focus just on the 1/2 first. So sine, if we remember, is opposite of hypotenuse. So sine of pi over 6 would give us 1/2. Okay, so pi over 6. But since it's negative, we want it to be the negative pi over 6 there. Okay, so that's our answer. Okay, very good. All right, how about letter B? Arc cosine of 0. What do we say for that? Arc cosine of 0. So in other words, cosine of what gives us 0? Well, pi over 2, pi halves, exactly right. Pi over 2, pi halves. Okay, very good. So, yep, pi over 2. Okay. How about the arctangent of root 3? Or in other words, tangent of what? Tangent of what gives us root 3? Okay, so, all right, Long, what do you say? Pi over 3? Okay, what are you going to say, Sean? You have a question? So 3 pi over 2 would work if it was in the range of cosine. Cosine goes, the range for arc cosine is from 0 to pi. 0 to pi for you. So 3 pi over 2 would be outside of that. Okay, for these inverse trig functions, you're not going to have multiple solutions. You're going to have just like one solution for these particular angles, or for these particular ratios. You're going to have one angle that results in that particular ratio. So yeah, so it would just be the pi over 2. Okay. Certainly, yes, if we go backwards, though, cosine of 3 pi over 2 would give us 0, but the pi over 2 is like, you want basically like the closer angle to 0. So the lowest, smallest angle, so pi over 2 that does that. Okay. But yeah, pi over 3 for arctangent of root 3. Again, if that's still like, whoa, how'd you get that? Well, again, root 3, arctangent, right? So that means tangent of what gives you root 3? Well, tangent of pi over 3 is opposite root 3 over adjacent 1, right? Tangent of pi over 3 is root 3 over 1. And so then pi over 3 is our angle there. Okay? How about arc secant of 2? Arc secant of 2. What do we say there? So, Bryce? Pi over 3. Very good. Yep, that is pi over 3. Okay? If that's like really throwing you off here because, we could use these, well, you could use a couple things here. You could use Choshikow, right, if you wanted to. So secant is hypotenuse over adjacent. Okay? So when we do hypotenuse over adjacent, hypotenuse and 2 over 1 there, and so that would be the pi over 3, right? Hypotenuse 2 over the adjacent side 1. Okay, you could also, rewrite it if you wanted to and write, okay, arc secant of 2 equals some angle theta, which means that 2 equals the secant of theta, or reciprocal, 1/2 equals the cosine of theta. So asking the arc secant of 2 is the same thing as asking cosine of what gives us 1/2 there. And so then we can see, okay, it's going to be the pi over 3. Okay. All right, how about arc cosecant of root 2? How about arc cosecant of root 2? What do we say there? Shelby? Pi fourths. Yep, pi over 4. Okay. We can do a similar thing like we did with the arc secant, right? Arc cosecant of root 2 equals theta. So that means root 2 equals cosecant of theta, which means that 1 over the square root of 2 is equal to the sine of theta. If we go back up to our reference triangles here, sine of pi over 4 would give us 1 over root 2. So the angle's pi over 4 there. Okay, good. Excuse me. And then how about arc cotangent of negative 1? How about arc cotangent of negative 1? What would that be? All right, Shelby, go for it. 3 pi over 4, but in the I guess with negative pi over 4, exactly right. In the context of these inverse trig, we want to just make the negative version there. So negative pi over 4, exactly right. Okay. So, boy, that was fun, wasn't it? Okay, so maybe we need to refresh our memory some on that, but that's okay. That's okay. You still have time. Remember, our test is not until Friday of next week, so you have time still to remember that, refresh your memory a little bit here. Of course, we also, if you remember, we used inverse trig to evaluate things like this, where if we said that y was equal to the arc sine of x, we wanted to find cosine of y, right? So if you remember situations like this, that sometimes it would look, another way to write that would be this way. Whoops. Make sure I write it correctly here. Cosine of the arc sine of x, right? So finding cosine of y, if y is equal to arc sine of x, is the same thing as finding cosine of the arc sine of x. Right? And we did stuff like this before where we drew like triangles and things, right? We evaluate, okay, if y equals the arc sine of x, that means that the sine of y is equal to x, right? If you take the sine of both sides here, sine would cancel out the arc sine and give you x, and then sine of y gives sine of y. And so we could then like draw a right triangle here, put the angle y in that right triangle because we're taking the sine of y, so y's got to be an angle. And so then according to our ratio here, right, sine is opposite x over hypotenuse 1, like that. But we're interested in the cosine of y, and to find the cosine of y, we need the adjacent side here. And we can find that adjacent side using Pythagorean theorem, right? So we can say, all right, question mark squared plus x squared equals 1 squared. And so question mark squared equals 1 minus x squared. And so the question mark is square root of 1 minus x squared there, right, if we square root both sides. Right, ringing a bell, hopefully. Okay. So then, using this information, we set up this right triangle, and then we want to find cosine of that y. So cosine of y is adjacent, root 1 over x, root 1 minus x squared over 1. So cosine of y equals root 1 minus x squared all over 1. Or just root 1 minus x squared if you want to. Okay? Let's try letter B here. So letter B, questions on A before I move on. I guess I should ask some questions. Questions on A. Okay. So letter B, let's again continue our little review here. So same idea, right? Except now we have y equals the arc secant of root 5 over 2. We want to find the tangent of y. So in other words, we're really trying to find the tangent of the arc secant of root 5 over 2. Oops. Like so. Okay. So let's go ahead and, I'll rewrite this. So if y is equal to the arc secant of root 5 over 2, that means the secant of y equals root 5 over 2. Keep doing that. There we go. Secant of y equals root 5 over 2, which means we can draw a triangle to help us out here, a right triangle. Put y in as one of the angles. Secant, well, again, if you remember Choshikow, it's hypotenuse over adjacent, but of course we can do the reciprocal here to both sides and say that's cosine of y equals 2 over root 5. Okay, and so cosine is adjacent 2 over hypotenuse root 5, and I'm going to let you finish the rest. Okay, so go ahead, finish off the problem there. Find the tangent of y, given that. Okay? So go ahead and find the tangent of y, using that given information. All right, so what we get for our answer, tangent of y is 1/2. Very good. Okay, so hopefully that's cleaning out the cobwebs a little bit here, right, with that inverse trig. And of course, this is stuff that we're bringing into calculus, right? There's no calculus here involved whatsoever. So we're going to add some calculus to it now. And so the reason why we refresh our memory here is because there's probably going to be some, evaluating of inverse trig functions, potentially having to rewrite things too if necessary. So this is why, we kind of reintroduce this, just to kind of refresh our memories a little bit. It's been a while since we've seen it, okay? So turn the page, and now we'll get into some calculus. Okay, now we'll finally get into some calculus. All right, so we want to find the derivative here of the arc sine of U. By the way, once we've completed this section right here of the notes, we will have learned all of the derivatives for which you will be responsible. So that's kind of a milestone right there, right? Okay, all of these this now will finish off the list of derivatives for which you'll be responsible to learn, okay, and to know. So that's good news. But anyway, so derivative of the arc sine of U. What is that, right? Well, before I just give you what it is, let's think about this function here, the arc sine. Okay, if you'll permit me, I'm just going to rewrite that as y equals arc sine of x for right now, and then we'll worry about with U. Okay, so let's just write y equals arc sine of x. So writing that as a function, right, if I were to go ahead and take the derivative right now, I'd be stuck, right? I can take the derivative of the left-hand side, no problem. The derivative of y with respect to x is just dy dx. But the derivative of arc sine, we don't know that one yet. But we can rewrite this function so that we can take the derivative, right, which we've seen in the past. So we can, sometimes take a function whose derivative we can't do, rewrite it to an equivalent function form, and then into a form where we can take the derivative. And that's what we're going to do here. We take sine of both sides, we get sine of y equals x. Okay, so these are equivalent. Do we know how to take the derivative of sine? Yes. Okay, so we're going to take the derivative of this with respect to x. You can see, when we go to take the derivative of this with respect to x, what kind of differentiation are we going to be using here? Implicit differentiation, because we have, kind of like we're taking the derivative of sine of y there, so we're going to end up with a dy dx. Okay, so the derivative of this, okay, well, we take the derivative of the outermost piece first. The derivative of sine is cosine of y times what? dy dx. Okay, equals, and then the derivative of x with respect to x, 1. There's the derivative. Okay. We'll then move the cosine back over to get the dy dx by itself. Okay. We'll move that over to get the dy dx by itself. But now it's like, all right, well, we started with arc sine of x. We end with 1 over the cosine of y, which is not typical. Typically, if we start with x's and we take the derivative of something, we end up with x's as well, right? So this is kind of weird that we start with arc sine of x, we end with 1 over cosine of y, and so maybe we can rewrite this somewhat, and in fact, we can. So we can set up a triangle based on, I guess, this information right here, that the sine of y is equal to x. So using that skill, that technique that we just used and we were evaluating inverse trig, sine of y equals x, so we'll set up a little right triangle here with y as an angle, and since that's x, we can say, okay, it's going to be opposite as x over hypotenuse of 1. Right? So this right triangle, right here, if you took the sine of y, it would give you x over 1, or x. Okay? And using Pythagorean theorem, we can get this missing side right here. So let's see, it would be, 1 squared equals x squared plus, I don't know, I'll say b squared in this case. We want to get the b. So we'll subtract x squared. We get 1 minus x squared equals b squared. Or in other words, b is just the square root of 1 minus x squared. So our missing side here is the square root of 1 minus x squared. Just like that. So instead of writing 1 over the cosine of y, according to this right triangle here, right, which we got from sine of y equal to x, sine of y equal to x gave us this. What is the cosine of y going to be according to this? What is the cosine of y equal to according to our right triangle there? The square root of 1 minus x squared, right? Cosine is adjacent. Adjacent to y is square root of 1 minus x squared over 1. So this, instead of saying cosine of y, I can say 1 over the square root of 1 minus x squared over 1, or just the square root of 1 minus x squared. So long story short, the derivative of the arc sine of u is 1 over the square root of 1 minus u squared times then u prime, of course, if for the chain rule stuff there. There's our derivative. The square root of 1 over the square root of 1 minus u squared times u prime. Okay? We saved some of the more complicated derivatives for last. Yay. All right, so there it is. Yes, question?
But isn't it all over and all implicit to in respect to x? So the u just represent the x?
So it would be like, you could think of it as like du dx if you wanted to. So I see what you're saying. I mean, it's yes, yeah. Yeah, exactly. Okay. So there it is. All right, questions on any of that? So I'll write that down there in our table. I'm not going to prove these other ones, but they're similar but not the same, okay, in format here. So the arctangent, derivative of arctangent is u prime over 1 plus u squared. Okay, the arcsecant, u prime over the absolute value of u times the square root of u squared minus 1. Okay. So, it's like these are close, but they're close enough that it's going to be tricky, to get these all down. We have like square root of 1 minus u squared, and then here it's absolute value of square root of u squared minus 1, like just the order slip. And here it's like 1 plus u squared without the square root. So, want to be very careful here. The good news is arc cosine, arc cotangent, arc cosecant. The good news is those are just the opposites of their non-co-function, brothers or sisters there, okay, siblings. So, in other words, arc sine of u, okay, is positive u prime over the square root of 1 minus u squared. Arc cosine is just negative u prime over the square root of 1 minus u squared. So that's nice. And then same thing with arc cotangent. It's negative u prime over 1 plus u squared. And arc cosecant is negative u prime over the absolute value of u, square root of u squared minus 1. Okay. So that's the good news. Really, it's 3 that you have to really know, and then you just do the negatives of those for the co-functions. All right. And that concludes all of the derivatives for which you will be responsible. On page 179 in your book is a nice table that summarizes all of the derivatives that you should know up to this point. Okay? 179 has all the derivatives that you will need to know up to this point on it. Okay? So you can use that there as a study tool if you want. They're all nicely organized right there in their chain rule formats. Questions on any of that? All right, so let's actually do some of these derivatives then, right? So arctangent of 3x. All right, so in this scenario, right, we know how to take the arctangent of u. So what is our u in this derivative? The u is the 3x, right? And so when I go to take the arctangent, it's going to be 1 over 1 plus that u squared, so the 3x quantity squared, times u prime, right? Which is just what? 3. Okay? So we end up with 3 over 1 plus 9x squared. If we simplify. Okay? Again, this is a perfectly fine answer. Just said differentiate. We did. Right there. That's the the derivative. But of course, we can simplify some. Okay? Questions on that first one? Letter A there? Sean?
It says u prime over 1
plus u squared. Mm-hmm.
I don't understand
Why did I put a 1 there? I multiplied by the u prime out here. It's so the u this is equivalent to saying 1 over 1 plus u squared times u prime, right? Just like that's like maybe a more obvious version of the chain rule, but they write it this way just because it's like, well, when you multiply this, the u prime will end up going up in the numerator there. That's all. So I'm glad you asked that because that is a little. Oops, yeah, there it is. That is a little like, strange that they do it that way, but I think it's just for simplicity's sake, although I think it makes it more complicated sometimes. Yeah, but it's just really just application of the chain rule. That's all. Okay. Arc sine of the square root of y. Again, my recommendation here, change that square root symbol to be y to the what power? 1/2. And I'm going to even put parentheses around it so it's more obvious, okay, what's, where that is. That square root is, inside the arc sine. So what is our u in this case? Y to the 1/2. Okay, so the arc sine, remember that was the one we proved, okay? So it's going to be equal to 1 over the square root of 1 minus our u, so it's y to the 1/2 squared. Okay, so there's the arc sine part. 1 over the square root of 1 minus our u, y to the 1/2 squared, times 1/2 y to the negative 1/2, right? The derivative of y to the 1/2. There's our u prime right there. So the derivative of y to the 1/2 is 1/2 y to the negative 1/2. We could stop there. We've taken the derivative, but we can also simplify, right? So maybe we should do that. So the square root of 1 minus y to the 1/2 squared becomes just what? Y. Yeah. Times. I'll change that y to the negative 1/2 to be 1 over 2y to the positive 1/2, which we can then multiply those denominators and numerators. So we have 1 in the numerator and then a 2. I'll change that y to the 1/2 to be the square root of y times the square root of 1 minus y. Okay. Now, we have one more little simplification we can do. Since the square root of y and the square root of 1 minus y, we're multiplying those, we can actually combine that together to a single root. And so it's 1 over 2 times the square root of y minus y squared. Okay, the y and the square root here can combine together with the 1 minus y and the square root here because it's a product. So you just distribute it. Y times the 1, y times the y, so y minus y squared. And that is our simplified derivative. Okay, simplified derivative. Yep.
Do we not have to worry about the fact that it's in respect to x?
Oh my gosh, I missed the dy. I even had that written down here. Sorry. Thank you, Carter, for pointing that out. Yes. Thank you for pointing that out. Okay. The good news is that doesn't. All we have to do is throw that back in there. But yes, thank you for pointing that out. Okay. So yes, it is with respect to x here. It is y in our function there. So when we did the derivative of 1/2 y to the negative 1/2, we had to further multiply by the derivative of what was inside. So the dy dx there. Okay. Yes. Be careful. Okay. Be careful there. Don't do what Mr. Witt just did. Okay. Yes, that is an implicit, in a sense, differentiation there. Okay. So yes, Shelby.
So it doesn't have to go on the opposite side. It can just stay on the same side.
Right. Exactly. And that's, I mean, again, so when it comes to this, the problem is like it's not really an equation. We have like an expression here. So there is no kind of like other side. I mean, yes, I'm using equal signs, but just more like equal signs as in they're all equal to one another kind of thing. Yeah. Yeah. Mm-hmm. If this were an equation setting, then yeah, you could move things around if you wanted to. Okay? All right, last one here. I will now check to make sure arcsecant e to the 2x, we're differentiating with respect to x. So this is not implicit differentiation. This is just a straight up derivative. So why don't you guys go ahead and give that a try? You've got your rule right here. You've got, what you're trying to do there. What is the u in this case? E to the 2x. So why don't you guys go ahead and give that one a try on your own? Okay, see what you can do. You've got the rule right there in front of you. Okay, and try to simplify it if you can as well. Okay, once you've got it set up, see if you can simplify it as well. Okay, it does simplify some. close here. Multiply the derivative of what was inside. So the derivative of 2x is equal to 2x. You have to multiply the derivative of what is inside that. Inside e to 2x is a 2x. So we're going to have 2 e to 2x there. By g. So the derivative of this is this again times the derivative of what's inside of it. 2 e to 2x. You see what I'm saying there? I know you were out, all that when we were doing all this chain rule stuff, so that's a mess. Did you see what I said? I said, the right, okay. Yep, the first thing said good first. Well, so a power raised to a power is these. And then I'll show you one more step. All right, so there's the first, the initial derivative, I guess I'll say. Okay, the initial derivative. But of course, then we can simplify that somewhat. So for example, I can bring that 2e to the 2x up in the numerator over the absolute value of e to the 2x, square root of e to the 4x minus 1, like so. Okay. Can we simplify any further here? Yes. Okay. What simplifies? E to the 2x. Okay. Why can we cancel those things out? I have this absolute value symbol around the e to the 2x here. But what do we know about e to the 2x? It's always positive, right? Because e is a number, right? It's like 2.67 something, I think. I may be wrong. But it's like 2 point something, okay? 2 point something. It's positive. Raised to an exponent, it will always be positive. And so these absolute value symbols are not necessary, okay? Will we always be able to just drop these absolute value symbols? No. Okay, but in this situation, since e to the 2x is always positive, oops, let me write that better. E to the 2x is greater than 0 always. Okay, so we can then just go ahead and drop these absolute value symbols, which then allows us to cancel out there and say 2 over the square root of e to the 4x minus 1. Okay, and so that is our final answer right there. All right. So, if the u here, if you are unable to guarantee it will always be a particular sign, then you cannot just drop the absolute value symbols there, right? So if you're unable to guarantee it will be always a particular sign, either positive or negative, then you can't just drop those absolute value symbols there. All right, you'll have to keep them. All right, and you won't be able to simplify like we just did, okay? Because they'll still have the absolute value symbols around it. All right, questions on any of that? All right, turn the page. So now we're going to start mixing in inverse trig with all the other derivative stuff that we've been doing. So, position, velocity, acceleration. We haven't talked about one of these in a little while, right? So the velocity of a particle is moving according to the function that v of t equals sine negative 1 t squared. What's another way I could read this as? Arc sine. Very good. Okay, very good. And this is confusing, and it should be confusing because it is. I can't argue with you there. We say sine squared of t squared, that's equal to sine of t squared to the 2. Whoops, it's off the screen. Right? Isn't that what we say? Sine squared of t squared equals sine of t squared to the 2. But when we say sine negative 1 of t squared, that does not equal sine of t squared to the negative 1 power, or in other words, 1 over sine of t squared. Right? That is confusing. Sine squared of t squared is the quantity sine of t squared squared. Sine negative 1 of t squared is not sine of t squared to the negative 1. Okay? This is arc sine. Okay, it is arc sine, not 1 over sine. Okay, that's confusing. And I don't know I mean, I don't know why we do it this way, but there it is. Okay, so apologies to that. Please don't get that confused. That is sine inverse or arc sine. Be careful taking the derivative of this, right? Because if you're not careful, you will want to take the derivative like this, using like just the chain rule, and ignoring the fact that it's an inverse trig function. That's going to completely throw off your derivative and really, mess you up for the rest of this problem. See?
Is there any way to say sine to the negative second?
So sine to the negative second would be what you would expect it to be, sine to the power of negative 2. I know. I see what you're saying, and I think it's dumb. Okay? But yeah, there it is. Okay? Yeah. So going back to our question, though. We have the velocity, and we want to determine is the particle's speed increasing or decreasing at time t equals 0. So how do we determine when a particle's speed is increasing or decreasing? How do we do that, Lander?
If the velocity and the acceleration have the same sign,
Okay, if the velocity and acceleration have the same sign, the speed is increasing. Exactly right. And then how do we determine if it's decreasing? If they have opposite signs. Right, exactly right. So we have to go about figuring out what the sign of our velocity is, SIGN of our velocity is, and what the SIGN of our acceleration is at time t equals 0. How do we go about figuring out the velocity at time t equals 0? Let's do that one first. What do we do? Plug 0 into the equation right here. Yeah, just find v of 0. So v of 0 equals sine inverse of 0 squared plus the square root of 1 minus 0. Okay. Okay. Are we supposed to square the 0 first, or are we supposed to take the sine inverse and then square our answer? So what should we do first here? Should we square the 0 first, or should we do sine inverse of the 0 and then square it? Square the 0 because it was originally sine inverse of t squared. You can imagine like the little parentheses around that t squared there. Okay, so yeah, square the 0 first. 0 squared is 0. Of course, the other direction would have been the same way, I think, but anyway. What is sine inverse of 0? Or sine of what gives us 0? 0. Okay, it's 0. Okay, plus the square root of 1 minus 0 is the square root of 1, which is just 1, and so we get 1. Okay, so v of 0 is 1. All right, great. We've got the velocity at 0. Now we need to figure out the acceleration according to what Lander said. So how do we figure out acceleration? Derivative of velocity. So we're going to take the derivative of this. So v prime of t, which is equal to a of t, will be, okay, and actually let me just rewrite here. I'm going to rewrite this to a more usable format, right? So there's our v of t written maybe in a better way. And if you want to rewrite it for yourself, that's not a bad idea too, right? All right, so the derivative of arc sine. Well, what's our u? T squared. Okay, so there's our u. Ooh, there's our u. Okay, so the derivative of arc sine is 1 over, right, the square root of 1 minus u squared. So t squared squared times u prime, which in this case would be what? 2t. 2t. Okay. So there's the derivative of sine inverse plus the derivative of 1 minus t to the 1/2. What would that be? So 1/2 times 1 minus t to the negative 1/2 times the derivative of what's inside, which would be negative 1, right? Don't forget your chain rule there. The derivative of 1 minus t is negative 1 there. I'm going to simplify this just a little bit. Not really necessary, I guess, but I'll go ahead and do it. So it's a 2t over the square root of 1 minus t to the 4th minus 1 over 2 times 1 minus t to the 1/2, or the square root there. Okay. Again, the negative 1 and the 2, the negative 1 times the 1/2. Well, negative 1 is going to make it a negative instead of a positive there. The 1/2, That leaves us with a fraction. And then the 1 minus t to the negative 1/2, that 1 minus t goes into the denominator with the 2. Okay, make it 1 minus t to the positive 1/2. And now we'll plug in 0. Okay, very nice here, because what's this first piece going to be? Just 0, right? It's 2 times 0 over 1 minus 0 square root of 1, so it's 0 over 1. And it's just going to be 0. Minus then, and then 1 minus 0 here is 1, to the 1/2 is still 1, times 2 is 2, so it's 1 over 2, or negative 1/2. So, is our speed increasing or decreasing? Or is our particle speed increasing or decreasing? Decreasing. So, write a sentence to summarize our results. The particle's speed is decreasing because v of 0 and a of 0 are opposite signs. And that should be sufficient conclusion there. Okay. Questions on any of that? Position, velocity, acceleration. Good stuff. All right, let's move on to number 5 then. Write the equation of the tangent line to y equals e to the arctangent of x at x equals 1. Okay, so to write the equation of the tangent line, what 2 things do we need? We need a slope and a point. Do we have either of those things in their entirety? No. How can we get our point? Plug in x into what? The original equation. That'll get us our matching y coordinate, so we get our point there. Okay, and then how can we get a slope of a tangent line? Derivative, and then do what? Plug in our point. In this case, we'll plug in the 1. So I'll go ahead and help you with the derivative here real quick, just to make sure we're okay. So y prime will equal the derivative of e to the something, e to that something, so e to the arctangent of x times the derivative of the arctangent of x, which is 1 over 1 plus x squared, and then times the derivative of what's inside the arctangent, but it's just the derivative of x, which is just 1, so there's your derivative. And I'll let you guys go from there. So go ahead, take it away. I got you the derivative there. Go ahead and come up with the equation of the tangent line. Okay? I just went through what to do there, right? So. Okay, so arctangent of 1, so careful, it's not equal to this. That is the derivative of arctangent of this. You just want to evaluate what is arctangent of 1, and then you e to that, right? So exactly, tangent of what gives you 1, and then you e to that, right? Gives your y coordinate. You're going to do both, right? Because you need to plug it into the original to get the matching y coordinate for your x coordinate for your point slope form, right? And then you can plug it into the derivative to get what? What do we evaluate the derivative to find for our tangent line? The slope of the tangent line. So 1 goes into the derivative to get the slope of your tangent line. 1 goes into the original function to get the matching y coordinate. So that way you have your point and your slope in the equation of tangent line. All right? Yeah. Yeah. You can't find any work. Yeah. Arctangent of 1. What?
It's not actually that bad. I think it's the second algebra.
It's not the bottom line. You're reading it, it doesn't feel as
How late? I mean, how many games? All right. There is the equation of your tangent line. Good job, guys. Questions on any of that? Questions on any of that? Almost. Almost, Mario. Flip over to the back. We have some blast from the past here. Oh, back. I'm sorry. So if you are ready to move on, I would like you to go ahead and I'll get back 1 second here. I'd like you to go ahead and try this example 6 here. Okay, go ahead and give example 6 a shot while I go back to the previous problem. One thing I'm going to say here, for what value of x is f continuous but not differentiable? On the interval, I'm going to give you an interval. On the interval, -6 to 6. Okay, so on the interval -6 to 6 is what I'm going to add there. Okay. I'm okay with leaving it for A, but yeah, we can say it the same thing if you want to there on the interval. -6 to 6 if you'd like. Yep. Okay, so add those two intervals to A and C, and go ahead and answer those questions as best you can. I'll flip back to the previous problem there, for the folks that still want to see or ask questions. Okay, I'll zoom in here too for you. Okay. Any specific questions on that, Emma?
I got the slope part.
Okay, you got e 1/2 or e to pi over 4 over 2. Great.
Then what do I do after that?
So again, to write the equation of a line, and we're going to use point slope form, right? I mean, you're okay with that. So point slope form, we've got the slope, we need a point, right? All we've got right now is x equals 1, though. That's not a point. That's just a single x coordinate. How do you find the matching y coordinate? Use the original function, plug 1 in there to get the matching y.
Why? That's in the top right.
Yeah, right here. So yeah, I'll kind of like... Okay. So again, I'll give you a minute or two to like kind of, work through some of these problems here. Some of these are, not inverse trig related, but it's still super pertinent, to calculus and stuff we've been doing. So. And I'm looking not only for the right answer, but also accurate and correct justification too, okay? So just the right answer, saying, oh, the function's not differentiable here, or the function's not continuous here, I'm looking for good justification for that. It doesn't have to be long justification, but sufficient justification. Actually, no, let's do this one. I'll kind of walk around to ask any questions. Yeah. Exactly. This is f, right? This is the graph of f. This thing is asking to find the derivative of f at the specific value of 3, since the x is replaced by 3. And so it's just, what's the slope there? Yeah, it's up 1, down 2. Yeah, exactly right. It's that simple, which is nice, right? Yes. So I also had the interval, I also went ahead and set the interval for f2. I would say, so I have no problem saying that f is continuous at -6 because we can talk about the continuity, like one side of the continuity and stuff like that. But when it comes down to here, we're not differential at these points, but I don't have a good argument necessarily, except for like the left hand and the right. I think the derivative. So that's why, anyway, just consider these being on the interval from -6 to 6, and this one also being on the interval from -6 to 6, but excluding the endpoints. Excluding the endpoints. So only include the stuff that's not the endpoints.
We already use the answer from
Not the endpoints where it's not. Oh, right. No, we're done. If you were like ready to move on and want to get into stuff, that's fine. If you're feeling good. Okay. All right.
too lazy to rewrite, so I'm just going to draw arrows.
So, letter A. For what value of x is f discontinuous? What do we say? Let's go to Sarah. What do you say, Sarah?
I said x equals 2 because
X
the
equals
limit
2.
does not exist.
The limit does not exist. Okay, yes. So at x equals 2, f is discontinuous. Okay, because the limit, actually we can even do this, because the limit, we can even use symbols here. Limit as x approaches 2 of f of x does not exist. Okay, did anyone go into talking about like limits from the left and limits from the right here at all? Okay, so I think that's even more thorough, I would say. So you can state this, and this is certainly fine, but I even like saying, you know, the limit as x approaches 2 from the left of f of x equals -2, which is not equal to 2, which is equal to the limit as x approaches 2 from the right. Okay, so giving that little argument, additional argument there, why do we know the limit doesn't exist, right? Because we can just say, oh, the limit doesn't exist, but how do we know the limit doesn't exist? The left hand and the right hand limits disagree, okay? So we can give the exact, reason why the limit does not exist there, okay? So, would that initial sentence be enough? Probably, maybe, I don't know. But, more thoroughly, we can say that additional piece right there too, okay? So, good job, though, Sarah. Thank you. Let's go to Lily. Lily, for letter B, what do you say is the limit there?
Working on it. I'm trying to remember the limit.
So do you recognize what this thing is asking, or what this thing
Yes,
is?
except for the h on the bottom. So like, for the top, I got 1/2 of x plus 1 minus 2.5.
Okay. So do you recognize this as the limit definition of the derivative?
Yes.
Yes, okay? We understand the derivative to be the slope of a tangent line, right? The one difference, though, is that normally we have x's in here, right? X plus h and x. So the 3 is replacing our x. So essentially what this is saying is, what is the derivative of f at 3? So, in other words, what is the slope of f at 3? And what is the slope of this piece of our graph here at 3? It's going to be a slope of 1/2, right? Up 1, right 2, up 1, right 2. So this is simply 1/2, okay? Simply 1/2. You can bypass all that trying to evaluate the limit stuff, and you can just say, this thing is asking me to take the derivative at 3 of my function f. If this is the graph of f, I can just find the slope at 3. Okay? Does that make sense, Lily? Okay, good. All right, moving on. let's go to Mario. Mario, for letter C, for what value of x is f continuous but not differentiable? And then explain how you know.
Is that x equals -2?
X equals -2.
Because there's immediate slope change.
Yes, okay, there's a sudden change in slope in the slope of the function of f, I'll say, at this point. Okay, sudden change in the slope of the function at this point. All right, and then lastly here, we're going to write the equation of the tangent line of g at x equals -1, given that g of x equals the arctangent of f of x. So this is just like we did before. Equation of a tangent line, we need a point and we need a slope. To find our point for g, we're going to plug that -1 into g. So it's g of -1, which is equal to the arctangent of the f of -1. Okay. What is f of -1? 1. And so this is equivalent to saying the arctangent of 1. And what is the arctangent of 1? Pi 4ths. Okay. In other words, tangent of pi over 4 gives us 1. So arctangent of 1 is pi over 4. Okay, so we have our point now, -1 comma pi over 4. And then what do we do to find the slope of our tangent line? The derivative. So g prime of x equals, this is a chain rule. Okay, so g prime of x equals 1 over 1 plus f of x quantity squared times the derivative of what's inside. The derivative of f is f prime of x. Okay, so we take the derivative of g there. It's the chain rule. The outermost function is arctangent. Derivative of arctangent is 1 over 1 plus our u squared times the derivative of what's inside, f prime of x. So if I want to evaluate then g prime of -1, 1 over 1 plus f of -1 squared times f prime of -1. Okay, plug the -1 in. What is f of -1? 1. So it's 1 over 1 plus 1 squared. What's f prime of -1? -1, right? At -1 on our function, the slope of our graph there is clearly -1, down 1, right 1, down 1, right 1. So it's just -1. And so we end up with -1/2. Okay? And so the equation of our line then is y minus pi over 4 equals -1/2 times x plus 1. Minus -1 is x plus 1, right? So there it is. Okay? Questions on any of that? If there are no questions, your homework is on the Google Classroom, so feel free to get started on that. Okay. The Goog. Question, and then I'll be right there.
So if I know I'm supposed to do exactly what we just did up there.
Yes.
On this one.
Yep.
And what's my first step for taking the derivative again?
What is the derivative of arctangent? Located on your table there.
Oh, I didn't even know it was right there.
Yep, it's in your table. Yep, or in your notes too. Bathroom, go for it.
Oh, can I go to the bathroom?
You may go to the bathroom too. That's fine.
Can I just leave it in terms of u, or is there like something I have to substitute in?
No, because what are you taking the derivative of in your case?
Do I just put it for x?
Use x instead.